So there are a couple of laws of thermodynamics. The first law of thermodynamics is the first law of thermodynamics, which is just kind of a boring name. So we often refer to this as there is no free lunch. So my kids used to go to a public school where the average income level is such that the school qualifies for everyone to receive free hot lunch. Is that lunch free? No. The children eating it don't have to pay for it, but somebody has to pay for it. Taxpayers pay for it. Now, is feeding children a good use of money? Yeah, that's a great use of money, but it's not free, right? There is no free lunch. And so we apply that to energy. The first law of thermodynamics is the law of conservation of energy. Another way to state this is the total amount of energy in the universe is constant. You can't get more energy. All the energy that there is all their energy that there ever will be, and all that there ever has been. So you can never design a system that will produce energy without using energy. You can't get something for nothing. People used to make money off of other people being gullible. And so you get these guys that would invent this perpetual motion machine, right? And it's like this thing that keeps moving without any input of energy. It's like, we could use this and, generate energy and do stuff. All of those things had some hidden source of energy. There is nothing that can keep moving, generating energy without taking energy from some other source. State functions. So think about climbing a mountain. She might, think that would be fun or just horrible. We're not actually going to do it, though. So here's this mountain, and what we're looking at here is elevation. How far above sea level are you? And so these people are going to climb the mountain, and you can take path A, where the path snakes back and forth so that you can climb without too much difficulty. And this path, you're going to walk 12 miles to get to the top of the mountain. Or you can take path B, which pretty much goes straight up the mountain. And here you're going to walk 5 miles. But this is going to be a lot harder because you're just climbing, right? You're climbing straight up. When these people who took path A and path B get to the top of the mountain, the change in elevation they have achieved is the same. They went from 0 feet to 10,000 feet. It doesn't matter which path they took, right? And you could imagine some other person over here who doesn't enjoy physical energy or physical exertion, and so they hired a helicopter. And they got in a helicopter and they flew up, and then they flew over here, and then they were lowered down onto the top of the mountain to meet the other people who hiked up the mountain. So this person traveled a different distance, right? They went up and over and down. But their elevation change is the same. They went from 0 to 10,000 feet. It doesn't matter how you got there. That is a state function. It doesn't depend on the path. It only depends on the beginning point and the ending point. Some things are state functions, some things are not state functions. The distance that you travel on path A or path B is not a state function. The distance people travel here is different, even though they end up at the same place. The distance traveled is not a state function. The change in elevation is a state function.
That's a constant.
Well, it's not a constant, it's just that it doesn't depend on how you got there. It doesn't depend on the path. It's not about the journey, it's just about the end. Okay? Other things, it's just all about the journey, and the end doesn't really matter. Anybody have any questions about this idea? So energy is something that's a bit hard to define because unlike the length of a piece of paper, where we have a definite beginning and end and we can measure it and we can define what zero length is, how do we define what zero energy is? It's like trying to, do velocity. Well, is that your velocity relative to the surface of the earth? Or is it relative to the sun? Because just standing on the earth, we are rotating. The earth is rotating at some crazy speed. And then the planet's also going around the sun, and so we're moving in two different directions, even though we're standing still. And so it becomes difficult. What do you define as zero? And so we have issues like that with energy. So we do a lot of looking at the change in things, because then we don't have to know what zero is. So internal energy is given the symbol E, and that's the sum of the kinetic and potential energies of all the particles that compose the system. We decide what we're going to define as the system. So the internal energy of a system is a state function. It depends only on the state of the function, its current existence. It doesn't matter on how it got to that state. So we can look at the change in internal energy, and we call that delta E. So this triangle is the capital Greek letter D, delta, and we use that to mean the change in. So delta E is the change in internal energy. And it's almost always defined as the final value minus the initial value. So delta E is the final energy minus the initial energy. And so like with the altitude, your change in altitude is your final altitude minus your initial altitude. So when we have a chemical reaction, we can look at the state of the reactants as the initial state and the state of the products as the final state. So here we have a reaction of carbon reacting with oxygen to form carbon dioxide, a combustion reaction. So the reactants here have an internal energy that's represented as this level. So we're looking at internal energy is increasing as we go up on the screen. So this has internal energy. When this chemical reaction occurs, the products are lower in internal energy. And so if we take the final energy and we subtract the initial energy, we get a negative number. So here, delta E is less than 0. And we're not going to worry about, well, what exactly is the number? We're just going to look at, is it larger than 0 or is it smaller? So this thing here is called an energy diagram. And we use it just to sort of help us visualize energy changes. It's a lot like an altitude diagram for a climb, where you're talking about, well, I started up here and then I went down the mountain, and so I could look and see what's the change in altitude. If I started at the top of the mountain and went down, my final altitude minus the initial altitude is going to be a negative number, right? That means I went down. If my change in altitude is positive, it means I went up. So this is a negative change in energy. That means that the system lost energy. Where did the energy go? Into the surroundings. So the system lost energy. The change for it in its internal energy is negative, meaning it lost energy. That energy flowed into the surroundings, the rest of the universe, and so the change in energy for the surroundings is greater than 0. A combustion reaction makes the surroundings hotter or colder? Hotter, right? You burn natural gas in your stove at home, and it gives off a lot of heat, and you can use that to boil water and make spaghetti, right? The combustion reaction is giving off heat. Where did that heat come from? It was stored chemical energy inside the natural gas. And in the process of the combustion reaction, that energy is released into the surroundings. And so the products of that combustion are lower in energy than the reactants were. So we can say that delta E for the reaction, the change in energy for the reaction, is equal to the energy of the products minus the energy of the reactants. And that change can be positive or negative, just like you can climb up or you can climb down. Here's another example. Here we're looking at no, that's the same slide. Here's another example. I pushed the wrong button again. This chemical reaction is the same substances, it's just written backwards. So here, instead of carbon and oxygen reacting to form carbon dioxide, we have carbon dioxide decomposing to form carbon and oxygen. Most chemical reactions can go in the forward or the reverse direction. So here, our reactant is CO2 that has a lower internal energy than the products, carbon and oxygen. And so when this reaction occurs, the products are higher in energy. So this higher energy minus the initial energy, we get a change in energy that's greater than 0. So the system is gaining energy. That energy has to come from somewhere. Where does it come from? The surroundings, right? So here, the surroundings are losing energy. Energy is flowing into the system. So delta E for the system is positive. Delta E for the surroundings then is negative. So the energy that's gained by the system is lost by the surroundings. And again, this is like me giving one of my kids money, right? I need money for gas. And, modern technology is awesome because I have the Bank of America app on my phone. And so he texts me, he's like at the gas station, right? And he realizes he doesn't have any money in his account. Mom, can I have some money for gas? And I just push a couple buttons and I can give him $50, right? And just bang, because it's a van, and right now 50 won't even quite fill it up. But I can just transfer that. So the money leaves my account and goes into his account. It's a negative for my account, it's a positive for his account, right? That makes sense. Same thing happens with energy. One thing, the system loses energy, that energy goes into the surroundings. The surroundings gain the same amount of energy that the system lost. Does that make sense? So we can say that the change in energy for the surroundings is equal to but opposite in sign for the change in energy of the system. The amount of energy being transferred, gained by one, lost by the other, is the same amount, but the sign is different, right? So summarizing energy flow. If the reactants have higher internal energy than the products, then delta E for the system, the change in energy for the system, is negative, and the energy is flowing out of the system into the surroundings. If the reactants are lower in energy than the products, then the change, when that reaction occurs, is positive, and the system is gaining energy from the surroundings. So the way to remember this, because it's a little confusing with the negative sign, which one's negative, is you think, I am the system, and this energy is coming in, is like money coming into my wallet. That's a positive thing, right? I feel positive about it, and it also goes positive on my account balance. Money leaving the system is negative for the system, because like money going out of my checking account, regardless of how I feel about it, my balance is going down, right? Mm-hmm.
So, for right here, shouldn't the surrounding be negative?
Oh, that's a good question. So, in this equation here, it looks like the system is negative and the surrounding is positive, right? But what this means is that they are opposite in sign. So if the surroundings in this example are negative, so maybe let's say this is no, that's not what I wanted either. Minus 50 joules. Well, then over here I have minus 50 joules, which is positive 50 joules. Okay, so it's just that the sign is opposite. It's whatever it is, the other thing is that times -1. And that's something that we're going to do some calculations and stuff where people get really messed up by that. Anybody else have any questions about that? So, conceptual connection. Consider these fictitious internal energy gauges that describe the initial conditions for a chemical system and its surroundings. So here's the chemical system, and here's its surroundings. So the chemical system's 3/4 full, the surrounding is 1/4 full. Which of these energy gauges, A, B, or C combinations, correspond to the final conditions following an energy change in which delta E for the system is negative? So if delta E for the system is negative, is the energy gauge for the system getting more full or less full? It's going to be less full, right? So here, this one is getting more full, so it can't be that one. And here, for A and B, come on, pointer, A and B, now the system is half full, right? Well, if the system lost 1/4 here, what happens to the surroundings? It has to go up 1/4, right? So this one down here is not possible because if the system lost this much energy, it's not possible for the surroundings to be the same. Because when we talk about a system and a surroundings, we're dividing the universe into 2 sections. The system and everything else. And so we can't say, well, the surroundings didn't get the energy, but something else did. There is no something else. The surroundings is everything else. So it can't be this one either. It must be A. One goes up, the other goes down by the same amount. Any questions? So heat and work. So heat and work are both processes by which energy can be exchanged. So we've got our system and we've got our surroundings, and we can have energy go from the system to the surroundings or from the surroundings to the system. How does that happen? Well, it happens either through heat or work, or many times both of them at the same time. So we use Q to represent heat. I have no idea why, but there it is. Q is heat. And we use W to represent work, so that makes a little more sense. Heat and work are not state functions. Those are more like the distance traveled when you make that change in elevation. They do depend on the path. The final and initial internal energies do not depend on the path. They just are state functions. So Q and W are not state functions, but the change in energy is equal to the sum of the heat and the energy. The heat and the work. The heat and the work. So we have sign conventions for heat and work. So heat is transfer of energy due to changes in temperature. And so Heat is positive if the system is gaining thermal energy, and it's negative if the system is losing thermal energy. So that goes along straight with the change in the energy itself. If you're getting it, it's positive. If you're losing it, it's negative. Yeah, endothermic and exothermic are heat in and out. Yeah. So work, we have to think of a little bit differently. So work that is done on the system or work that is done by the system. So, I don't know, maybe a massage, right? So if someone does a massage, does work on you, and they're rubbing your shoulders and stuff, that's a positive experience for you, the system, right? But if you are the massage therapist doing the massage, you're having to put out, that's work, right? It's sort of a negative experience. You're giving out to do that. So when you do work, it's negative. When work is done on you or for you, it's positive. That makes sense? Change in energy flowing into the system is positive, out of the system is negative, like money. Oops, keep pushing the wrong button. So here we're going to look at those billiard balls again. This is a good pool table that has a nice smooth surface. Now, in any real life situation, you have a ball rolling across a surface, it's going to slow down, right? And how much it slows down just as it rolls is going to depend on the surface that it's rolling on. If it's rolling on something very, very smooth, the ball will roll much farther with the same amount of energy than if it's rolling on something that's very rough. So think about rolling a tennis ball on a concrete sidewalk versus rolling a tennis ball on grass. Which one will the ball roll farther on? On the sidewalk, right? Tennis balls don't roll very well on grass. You have to give it a lot of energy to get it to roll on the grass. If you gave it that same energy on the parking lot, it would go a long, long ways, right? Why? Well, there's friction. So as this ball is rolling across the table, it's experiencing friction with the table, and it's losing heat energy. Heat is being lost as it rolls, and so it's going to slow down as it rolls across. So here we have initial kinetic energy for this ball is 5 joules. In the process of rolling across the table, it's going to lose half of a joule before it hits the purple ball. That is heat. That's one way of transferring energy. When the ball hits the purple one, we have a collision, a force acting through a distance, and we have work being done by the white ball onto the purple ball. And if it transfers all of its kinetic energy to the purple ball, now the kinetic energy of this ball is 0, and so it transferred 4.5 joules of energy to the purple ball. So the work, the white ball is their system, work is minus 4.5 joules, heat is minus half a joule, and the overall change in energy is minus 5 joules. It went from 5 to 0. Final minus initial, 0 minus 5 is minus 5. So the surroundings here include the purple ball and the table, because energy is being transferred to the table and to the purple ball. If we have a rough table, and we start out with this ball with the same amount of kinetic energy, 5 joules, as it rolls across the rough table, is going to lose a lot more energy through heat, 3 joules. This is an abused pool table. It's been out in the yard or something, and it's all roughed up, and it's not very fun to play on because you hit the balls and they just don't roll very far, right? It's like, this is no good. So it loses 3 joules of energy. It only has 2 joules of kinetic energy left when it hits the purple ball, and so it does less work on the purple ball. So the work done is -2. The heat transferred is -3. The total energy change is the same. The total energy change is a state function. It doesn't matter if it was a smooth table or a rough table. The change in energy is the same. But the heat and the work are different. The heat and the work do depend on which table it was, right? Depends on the path. So here we can look at the change in energy for the system, for the white ball, and the change in energy for the surroundings, which is the purple ball and the table. The energy lost by the system, it lost 5 joules. And so the energy gained by the surroundings is -1 times that, +5 joules. Any questions? Yeah, I kind of said this already. So heat and work are not state functions, but the sum of those two is going to be the same, because that's the change in energy, which is a state function. Okay. A cylinder and piston assembly, defined as the system, is warmed by an external flame. The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward against an external pressure. If the system absorbs 559 joules of heat and does 488 joules of work during the expansion, what is the value of delta E? The negative signs here can be very confusing. They are also very important. And so, as in this problem, direction is often indicated using words. And we do that in real life too. We say, well, I earned $5 or I lost $5. We don't say I paid -$5, right? Because I paid means it went out. So I don't need to specify direction with a negative sign. In your bank balance, where it's looking at all the transfers, there's going to be positives and negatives, right? Because there's no words there to tell us direction. So here we've got these numbers, and the direction of this energy transfer is indicated by the words. So let's pull these numbers out. I've got 559 joules. It says that's heat, so I'm going to call that Q, because that's the symbol for heat. And 488 joules is work. Now, it doesn't say -488 or -559, but I can't just assume that they're positive. I need to think about this. So it absorbs heat. If I absorb money into my account, is that a positive or a negative? That's positive. So we don't really need the positive sign here, but I'm going to write a positive sign just to emphasize that this is positive. And the system does work on the surroundings. There's doing work and having someone do work for you, which is more pleasant. Having someone do work for you is more positive for us, right? This is doing work for something else, and so this is negative. So we're asked for the value of delta E. Delta E is the sum of Q plus W. So if we want to find delta E, we have to know the direction of these two energy transfers. And we figure them out from the words. So Q is 559 joules plus the work is -488 joules. 71. Now, you can overthink that when you're trying to do the math and come up with the wrong answer. You can also just type it into your calculator exactly the way it's written, and your calculator's going to know what you mean. 559 plus negative 488. Not plus minus. There's a minus button, and there's a change sign button, a negative button. And you should get 71. Any questions? $71 joules.